So this next unit is going to be on naming compounds, and we're going to start by naming ionic compounds. And I just want to start with a little bit of review, which is why do ions have the charges that they do? So hopefully you remember this term isoelectric, which is same number of electrons. So atoms or elements gain or lose electrons to be isoelectric with noble gases. Okay? So, how do we name ions? Here, and you're going to see this set up kind of a lot, where I have like some examples and then some questions here. So every time I go to a new page, I'm going to ask you to pause. I'm going to ask you to think about these questions and try to answer them. So go ahead and pause now, see if you can answer these questions in your notes, and then we'll fix as we need to. What type of elements have a positive charge? Well, lithium, sodium, calcium, magnesium, those all have positive charges. And if I look at the periodic table, lithium, sodium, potassium, these are all over here. These elements tend to have positive charges. These elements tend to have positive charges. Even these elements tend to make positive charges. So the types of elements that tend to make positive charges are metals. What types of elements have negative charges? Well, nitride, phosphide, oxide, chloride. So that looks like nitrogen, oxygen, fluorine, chlorine, sulfur, selenium, bromine, iodine. These are all over here on this side of the stair step. So these are all nonmetals. How are the numerical charges determined? Well, that's distance from noble gas, right? So for example, magnesium's closest noble gas is neon. So magnesium needs to lose 2 electrons to be isoelectric with neon. Electrons have a negative charge, so magnesium ion has a charge of +2. All right, how are the cations named? It's the element name, plus ion. Now notice that that ion plus ion is actually really important, because if you don't have that, then what you've just said is the element name, and you haven't indicated that it's an ion. Okay, well, that's simple enough. How are the anions named? Well, when you look at this list, all of these end in IDE. Okay, so we say that that is the root of the element, and then IDE. And then, of course, this is an ion, so you need to include the word ion. That's naming ions. So if I wanted to, for example, do the ion that tellurum would tend to make, why don't you give that a shot? Tellurum's number 52. See if you can figure that one out on your own. So tellurum is 2 away from xenon, so it's going to gain 2 electrons. So would become Te2 minus, which would make it an anion, which would make it telluride ion. Huh, that's funny. Okay, so great. Let's take a look at this page. So I have another set of compounds here, both their names and their formulas, and I want you to answer these questions. So the first question is, look at your periodic table, identify the two types of elements that make up these binary compounds. I have a metal, so lithium, sodium, calcium, magnesium, potassium, magnesium, magnesium, calcium, strontium, and I have a nonmetal. Okay, which type of element is listed first? Well, that's pretty simple. It's the metal. Is there anything unusual, excuse me. Is there anything unusual about how the first elements are named when naming the compounds? Well, I mean, looking at this is lithium, that's sodium, that's a no. Is there anything unusual about how the second element is named when naming the compound? Well, if I look at it, it's named like anions. So that is root IDE. Okay, great. Ooh, now here's the tricky question. Why are the elements in these compounds combined in different ratios, as shown by the subscripts in the formulas? Your periodic table will be useful here. Well, hopefully you thought about this one. And I'm going to talk about K3N because that one's interesting. All right. So we're going to be doing something called writing charge balance equations. Okay. So I start here with potassium ion, and I have 3 potassium ions. And those 3 potassium ions have joined up with 1 nitride ion, which is N3 minus. So I have a total positive charge of 3K plus, so that's 3 positive, and I have a total negative charge of negative 3. And positive 3 and negative 3 equals 0. So the elements are combined in these ratios in order to cancel charges. And this is really important, okay? For a compound, the net charge is 0. And that is really, really important. Now, the term net here means just total or sum, the sum of the charges, okay? So for a compound, the net charge is going to be 0. That is really super important. You should really know that and not get messed up by it. So again, they're combined in different ratios to balance out charge. Okay, so let's move on to the next one. Oh, okay. Sorry, before we move on to the next one. So let's talk about how we can convert from either names to formulas or formulas to names, because you'll be doing both. Okay, and it's very, very similar steps every single time you do this. Okay, so let's take an example compound, calcium nitride. Well, the first thing that you have to do is identify the type of compound. Okay, and I'm going to show you a sheet that you can use as to help you as you're learning. You won't have it on assessments, but it does help you figure things out. So the first thing that I have to do is I have to identify the type of compound. Well, this looks like a binary ionic compound because it looks like I have two elements. Sure. So the next thing that we have to do is we have to write a charge balance equation. So what is the charge of calcium ion? Calcium ion has a charge of 2 plus. And what about nitride ion? Nitride ion has a charge of 3 minus. All right, so we need to balance the charges. And one of the things that I'll talk about with people here is using the least common multiple of like the absolute value of the charges. So I have a 2 and I have a 3, which means the least common multiple here is 6. So that it would take me 3 calcium ions to get to a positive 6, and it would take me 2 nitride ions to get to a negative 6. Okay, so then so there's my charge balance equation. When I take that and I turn it into a formula, the formula just becomes Ca3N2, where each of these, we'll call them coefficients in the charge balance equation, go down to subscripts. They mean basically the same thing. In the charge balance equation, it means that I'm combining 3 calcium ions and 2 nitride ions, and I get this chemical formula, which has 3 calciums and 2 nitrogens. Okay, so that's converting from name to formula. So now we'll do formula to name. So the first thing that we have to do is we have to identify the type of compound. So this is a binary ionic compound, which I can tell because it only has 2 elements. We're going to add on to these later, but for now, it's got 2 elements. Okay, the first one of them is a metal. Okay, and I guess we need to add that up here. One of them is a metal. Then we write a charge balance equation. Well, I've got 2 iodide ions. Okay, and so iodine is down here. It has a charge of -1. And I've got magnesium ion, which has a charge of +2. That's right here. Has a charge of +2. So there we go. The nice thing about this is that the charge balance equation is pretty easy to write here. So Mg2 plus 2I minus, and then you just name the cation, which is magnesium. And then the anion. So magnesium iodide. Now you might be thinking to yourself, Mr. Ryan, this writing out the charge balance equation thing seems like way overkill for what we're doing. Yes, that's true. Right now, that's overkill. But we are going to use the charge balance equation concept over and over and over and over and over again. So it's a good idea to really take the time to understand that and to get in the habit of doing it. Okay. All right. So here I have another group. So the part 3, these questions refer to how this group is different from this group. Okay, so these are the binary ionics that we've done before. These are a little different. So I want you to pause. I want you to answer all these questions, and then we'll come back and talk about it. So how are the element combinations of the new compounds on top similar to the old compounds below? Well, they still start with a metal. and they also have a nonmetal. Okay, now what's different? Well, what's different? Um, hmm, for that, I'm going to need to go to the periodic table. The first compounds were all in here. The metals were all in here. And now the metals are all in here. Ah, interesting. So what's different is the location of the metal. How's the naming of the new compounds similar to binary ionic? Well, when I look at it, I still see the name of the metal, although it does have like this Roman numeral here. Um, and then it looks like it also has the name of the anion as well. So it's still name of cation. And then what's different here is that there are Roman numerals. And then, so it's name of cation with a Roman numeral plus the name of the anion. All right. What does the Roman numeral in the name of the new compounds represent? Oof, oof, that's tough. Okay, well, let's actually take two examples and deconstruct them a little bit. So I've got CuCl and I've got CuCl2. Okay, so when I write a charge balanced equation for these things, something really pops out right away. So in this one, I have one chloride ion plus a copper. So the charge of that copper has to be +1 to balance the charge. Here, I have two chloride ions, which means that this can have a charge of +2. Huh. Well, that's really interesting. So these elements have more than one possible charge. And in fact, a lot of elements in the periodic table can have more than one possible charge, including the transition metals here, the heavy metals here, and then the F block metals as well. So a lot of metals actually do this. So what does the Roman numeral represent? Well, when I look at this top one here, where the copper had a charge of +1, the Roman numeral is 1. And here, where the charge of copper is 2 plus, I have a Roman numeral 2. So the Roman numeral gives the charge of the cation. All right, now these are going to be honestly a little tricky because if you think about it, the other ones were easy because we could use the charge of the cation to find the charge or to figure out how things balance out. All right. Now here it's going to be a little tricky because some of these metals have more than one possible charge. But this right here, this Roman numeral gives the charge of the cation. That's kind of the key of these. We're going to name these compounds as transition metal ionic compounds. Okay? So, let's talk about what things get named as a transition metal ionic. And actually, I'm not even going to do that. Gosh, that's crazy. I'm going to say most metals. And what I'm going to focus on instead is which ones get named as binary ionic. So, binary ionic compounds are any metals in the S block plus 3 that you just have to memorize, which is aluminum, zinc, and silver. Okay, now let's go to our periodic table. Okay, here's aluminum, here's zinc, here's silver. So if we look at this, they're like right next to each other. Okay, now the interesting thing about this, or the great thing about this, is that we can use aluminum. We can actually figure out aluminum's charge pretty easily. Aluminum's nearest noble gas is actually neon, so aluminum has a charge of +3. Okay, so not only do you have to memorize that these ones only have one possible charge, you also have to memorize what the charge is. Aluminum has a charge of +3, zinc has a charge of +2, and silver has a charge of +1. So let's go back. Aluminum has a charge of +3, zinc has a charge of +2, silver has a charge of +1. You have to know those, okay? All right, so those metals, the metals in the S block, and aluminum, zinc, and silver get named as binary ionic. By the way, the S block, you will also see me refer to those as group 1 and group 2 metals, just so you know. And then TMI, which is what I'm going to call transition metal ionic, is going to be everything else. All other metals, okay? It could be, you know, the metals over here, the metals over here in the P block, the metals over here in the D block, the metals in the F block. Any other metal is going to get named as a TMI. Okay? So let's do some. How are we going to do this? Well, the first thing that we have to remember, and you know it's important because I have written it in all caps, is that the net charge of a compound is 0. That is super important, and we are going to use that a lot here. Okay? Now, the first thing that we need to do is we need to identify the type of compounds. Now, identifying the type of compounds starts to get a little tricky here, okay? And I have actually, a student gave me this idea a few years ago where we came up with a little flow sheet that you could use to help you identify the type of compound. This is linked on Canvas, so you'll be able to find it quite easily. Tin 2 sulfide. So we're going name to formula. So when I look at the compound, I want to go name to formula. So are there numerical prefixes? No, we'll deal with that tomorrow. Does it end with an acid? No, we'll deal with that tomorrow. So it's ionic. Is there a Roman numeral on the metal? Yes, then it's TMI. So this metal is a transition metal ionic, okay? Because it has a Roman numeral in the name. Okay, so the next thing that we're going to do is we're going to write the charge balance equation. So I can get the charge of sulfide from the periodic table. It has a charge of -2. Now tin's down here. And I occasionally see people say things like it's got a charge of -4. No, I've seen some crazy stuff. Okay, could have a lot of different charges, but we have it right there in the name. Remember that the Roman numeral gives you the charge of the metal. So that's tin 2 is Sn2 plus sulfide ion, S2 minus, charge balance equation. Hey, look, it's already balanced. That's handy, huh? So my compound is just SNS. All right. So how about Fe2O3? Okay, so first thing that we have to do when we're going formula to name is identify the type of compound. So we're going formula to name, and we want to identify the type of compound. Now, Fe is a metal, that's iron. Okay, so we start with a metal. Are there more than two elements? No, it's binary. However, is the metal group 1, 2, or aluminum, zinc, and silver? Well, in this case, this one is not in groups 1 or 2, or aluminum, zinc, and silver. Okay, so remember I said groups 1, groups 2, so the S block, or aluminum, zinc, and silver. Iron's over here. It's not any of those, which means that we are going to name this as a TMI. Okay. So now, here's the key. Writing the charge balance equation for these is a little tricky. What you have to do is you have to use the anion to determine the charge of the cation. So what I do is below, I write the charge of each ion. And then above, I write the total charge. So we're going to use the anion to determine the charge of the cation. So the anion is oxide ion, so O, and that has a charge of -2. So each oxide ion has a charge of -2. There are 3 of them, so 3 times -2 is -6. Okay, now the net charge of a compound is 0. So if the net charge of a compound is 0 and I have a -6 charge, I have to also have a +6 charge. Okay, so now I've got 2 irons in order to get to a +6 charge. So I can kind of think of that as division, right? +6 divided by 2 means that each iron here has a charge of +3. And I can write my charge balance equation. So I know I have 2 Fe3 pluses plus 3 O2 minuses, and that makes this compound, Fe2O3. So now we just need to write out the name. Oh, write out the name with a Roman numeral. So this is iron, and we need our Roman numeral. And the Roman numeral, remember, represents the charge of the ion. So iron 3 oxide. Oh, hey, iron 3 oxide. Okay, and there we go. There is our compound. All right, now for the last group of compounds, and I know this is turning into kind of a long video, but that's okay. We're going to look at these, okay? Now these ones, you can immediately tell, look a little different, okay? So these ones, hopefully you noticed right away that all the other ones had just 2 types of elements. Now we've got 3 types of elements. Now a lot of these already still start with a metal, but now they have other things here. So these are called polyatomic ions. Remember, poly meaning many. So many atomic ions. Okay, so here's the deal. All right, I am going to give you a polyatomic ion sheet, which looks like this. Okay, and you will basically be able to use this for the rest of the year on every assessment. Okay, so you should probably print it out and kind of have it with you always and forever, like your periodic table. And you will see that I have a ton of polyatomic ions on here. Okay, I'm going to come back to this in a couple of minutes because there's one really important thing at the end that I want to talk about just for like a minute. But These are polyatomic ions. I give you the names, I give you the formulas with the charges. I'm not even making you memorize them because I'm so nice, okay? So all we really have to do then is we just have to use it. So let's go back. How do we do these? Well, boy, shocker of all shockers, the first step is going to be to identify the type of compound. So how do I do this? Well, let's go back to our compound sheet. And here we're going name to formula. We know we're ionic. And in this one, there's no Roman numerals, so there's no transition metal ionic. Now, does the anion end in ATE, ITE, or hydroxide or cyanide? ATE, IT. Oh, look, that ends in an ITE. And when we look at the polyatomic ions, you'll notice that most of them end in either ATE or ITE. You might notice that there are a couple like cyanide and hydroxide that are a little different. You just kind of have to remember that those are polyatomic ions. So that ITE ending tells me that I have a polyatomic ionic. Okay? So the next thing that we do is we write a charge balance equation. Well, potassium ion is K plus, and sulfite, I just get it from the polyatomic ion sheet. It's no problem. Sulfite, right there in the 2 negative column, is SO3 2 minus. All right, so to balance the charges, I need 2 potassiums. So I simply write K2SO3. All right, now you will see some that look like this, and you saw some up here that there are parentheses. Why are there parentheses? Well, let's kind of deconstruct this a little bit. Let's identify the type of compound that this is. So I know because I've got, now I'm going from formula to name. So it starts with a metal. Is the metal group 1, 2, or aluminum, zinc, and silver? No, which means that this compound is a TMI. However, we are not done yet, okay? Because there are 2 things here. There are 2 kind of branches in the ionic. Are there more than 2 elements? Well, yes, there are more than 2 elements. There's 1, 2, 3 elements, which means that I also have a polyatomic ionic. So keep in mind that transition metal ionic and polyatomic ionic is a combination that is possible, okay? Now, realistically, I could say that transition metal ionic and binary ionic is also possible. If you want to do that, I'm totally fine with it, okay? So, so the next thing that we're going to do, because I have transition metal ionics, is I'm going to use the anion to determine the cation. So phosphate is PO4 3 minus. Oops. So PO4 has a charge of -3. There are 4 of them. That gives me a total of -12, which means I have to have a total positive charge of +12. There are 3 tins to get me to +12, which means that each tin has to have a charge of +4. So now I can write the charge balance equation. So there are 3 SN4 pluses and 4 PO4 3 minuses. Okay, now this tells you exactly what these parentheses do. These parentheses are used to tell me that I have 4 of this polyatomic ion. So now I can just write the name, which is tin, and don't forget the Roman numeral here, tin 4 phosphate. And that's how you use polyatomic ions in your naming. So one last thing, real quick right at the end, okay? you may, oops, you may see something like the ion iodate, the name iodate, okay? You may well see that. So when I look at the polyatomic ion sheet, I don't see an iodate in here. So there are actually a couple of them that you need to be able to derive, and we're going to use the periodic table for this. Iodine is down here. It's similar to all these other things in group 17. So when I look on the polyatomic ion sheet, I'm looking for something that's either bromate or chlorate or fluorate. So when I look at the polyatomic ion sheet, hey, look, I see chlorate, which is ClO3 1 minus. Okay, so iodate is going to be similar to chlorate, which is ClO3 1 minus, which means that iodate is IO3 1 minus. Okay, so there are some that you might need to derive using the periodic table. And that is it for today. Good luck, my friends.